In this video, we examine the process through which statistics can help answer research questions and help shape and inform future research questions. Statistics plays an integral role in research as a tool that helps us to see whether something is real, whether something we think we see is in fact real or likely to be real, or just a coincidence or a false impression. You may be a teacher and see an intervention that looks like it's helping kids, but it's really not. Worse yet, there's a lot of people in education and the social sciences running around selling ideas or selling products that are complete bunk. They sound good, they look good, they may make us feel good, but it's bunk. Statistics helps us recognize it. It helps us debunk the bunk. In fancier terms, it can help us to detect the signal, reality, through all the noise that surrounds us. There are all sorts of different ways people conceptualize this process, but they generally share the following features. You start with a substantive question. You can think of this as an English language sort of broad general statement about what someone thinks is happening or will happen. Substantive questions are framed in ways like, does this program help kids with their math? Or does student mobility hurt children academically? They're nice, general conversational statements that reflect that underlying question in which we're interested. But notice it's not exactly telling us which kids we're talking about. First grade, fifth grade, 10th grade. And it's also not telling us how are we assessing math. Homework, standardized tests, GPA. So think of the substantive question as taking a 20,000-foot view of whatever you want to study. Once someone has settled on that general substantive question, it needs to be reframed in a way that more clearly operationally defines exactly what the question is. What I mean by this is that it's stated in a way that more definitively tells people exactly who we're talking about, what's being examined, how is it being measured. You can think of this as the statistical question because it more precisely restates the substantive question in a way that someone can actually measure and evaluate. For example, a substantive question like, does having a parent read to their child lead to improved reading skills in children? Could be reframed into a statistical question like, do 50 first grade children whose parent reads to them 30 minutes or more each day show larger gains in STAR reading performance scores than 50 first grade children whose parents don't read to them at least 30 minutes each day? Notice the statistical question tells us who the question's about. A total of 100 first grade students. It also tells us exactly what we mean by reading to their child. We mean reading 30 minutes or more each day versus less than 30 minutes each day. It also tells us how we're measuring reading. We're using STAR test scores. Ideally, a statistical question should be precise enough and detailed enough that someone else could take the same question and answering it the same way themselves using a completely different group of children. Based on how things are described in our statistical question, we go out and collect data and perform statistical analyses. We then draw some statistical conclusions based on that data. The statistical conclusions describe any differences or effect or pattern that we may have seen, and it indicates whether that difference, effect, or pattern likely reflects some true underlying reality or whether it may just be random chance fluctuations. the statistical conclusion gets at the question of whether the results are real. In future videos and future courses, we'll spend a lot of time talking about how to derive and interpret statistical conclusions. But for now, they can sound very technical with things like a mean difference of 0.30 grade levels was observed, which was statistically significant based on t with 237 degrees of freedom equal to 4.934 and p less than 0.001. Now, again, we'll get into what all of that means in later videos, but if you stick with it, you'll be talking that way yourself soon enough. Based on the statistical conclusion, we then draw a substantive conclusion that reframes the statistical conclusion in a more practical way and also incorporates any additional information or interpretation of the findings into a general statement of what was learned and concluded from the study. Continuing with this example, a substantive conclusion might be, the more parents read to their children, the larger gains one sees in reading skills. Now, the substantive conclusion can be different from the statistical conclusion. For example, the observed effect may be statistically significant and it may be real, but relatively small and unimportant. I may test an intervention and statistically conclude that it does help improve math performance. However, maybe the improvement is minuscule and the cost of the intervention is tens of thousands of dollars a year per child. One of the things we're going to learn is that if you have a large enough sample, just about everything is statistically significant. Another reason why substantive and statistical conclusions may differ is because you also see other effects or side effects that need to be considered. Maybe you're seeing this gain in math because you've also reduced the amount of time children spend in reading. And the result is that we see even larger reductions in reading skills than we see improvements in math. The substantive conclusion might be that the program does seem to improve math skills, but that the subsequent decline in reading skills just makes the program impractical for children. Either of these might result in a statistical conclusion that the program leads to improved math performance, but a substantive conclusion that the effect is too inconsequential or leads to too many other negative outcomes to be worthwhile. Another reason that substantive conclusions may vary from statistical conclusions is that you're aware of something else going on that's impacting your results. Years ago, a former colleague of mine, Annette LaGreca, was looking at stress in children who grew up in Miami. She did a study, and sure enough, she found a statistically significant increase in stress as children grew older. But she also knew that right in the middle of her study, the city had been devastated by Hurricane Andrew. So she had to build that into her substantive conclusions and instead needed to talk about the impact of disasters on children's stress. In that sense, Dr. LaGreca is also a great example of the last step in this research loop, in that she used her substantive conclusions looking at factors related to stress and resiliency to lead to new substantive questions. Why are some kids more impacted by stress than others? Why does it last longer for some and less for others? What can be done to reduce the impact of disasters on children? It was really a great example of turning lemons into lemonade, as she went on to become an international expert on the impact of disasters on children. Let's go through one other example to illustrate the connection and the differences between the substantive and statistical parts of this process before we move on. Let's say that I'm interested in the relationship between classroom size and student learning because I believe that children in smaller classrooms will learn more. My substantive question is that general query of, do smaller classes lead to improved learning in students? Now, to actually study this, I reframe that question into a statistical question, making it more precise and defined. For example, my statistical question might be, do 8-month gains in STAR math scores for 250 third grade students in Maine increase as their classroom sizes get smaller? Notice, I'm not just talking about generic students. I'm talking about third grade students. In fact, I'm talking specifically about 250 third grade students in Maine. And what did I mean by improved learning in the substantive question? I've now clarified that what I mean is 8-month math score gains on the STAR assessment. Okay? Now, let's say we go out and collect data from 250 third grade students and analyze their STAR assessments and classroom sizes, and we then draw our statistical conclusion, which might be that there was a statistically significant correlation of negative 0.15 between classroom size and math gains, with T with 248 degrees of freedom equal to 2.389 and P equal to 0.018. Again, that last bit shouldn't make any sense at this point. That's why you're here. But we'll be learning how to calculate and interpret these types of statistical conclusions in future videos. And going back to our example, based on that statistical conclusion, we make the substantive conclusion that smaller classrooms are in fact associated with larger math gains in students. And again, that takes us back to what I personally think is a key part to the entire process. Do these substantive conclusions inspire new substantive questions that build off the original study? For example, if we find that smaller classes are associated with larger reading gains, some follow-up questions naturally arise. For example, why do students in smaller classes do better? Is it more individualized instruction? Is it more help? Or maybe it's just a case of higher income families whose kids may show more gains live in upper income communities with smaller classrooms. Is there a point at which classes get to be too small and it actually hurts children's learning? That's where one substantive conclusion can lead to the next substantive question, and the whole process starts all over again. That's science. Okay? That's also a good point to wrap up this video. So, bye for now.